let's go ahead and get started. And just to remind you guys of what's going on here, last time I passed out to you guys a copy of your homework number 3 test review. It is due when? On Monday, which means our test is on Wednesday. And again, this is what we want you guys to do. You're going to turn in that copy that I gave you guys that you to work on, and then you should make another copy of this thing and bring a blank copy to class, because on Monday's class I'm actually going to go over it because I won't have time to get it graded and get it back to you guys before obviously Wednesday's class. So bring a blank copy with you so you've got something to study, and I'm going to make like I said, a video of me actually going over this entire homework set, making sure that you guys understand it. So your test is on Wednesday, and then we'll get back in the swing of things. But if you look at also to check out your Hawk stuff, what we got going on here, you got your quiz number 7 coming up. You've got your lessons and your certified from 4.3 and your 4.4 stuff, and of course we got our in-class test. So coming over here, pay attention to due dates. That's what I'm really trying to tell you. We're going to finish up what we talked about last time because we still got a couple more problems to do in the business application problems. And then from that, we're going to go ahead and move on into Chapter 5 because we got no time to waste. So we'll move on into Chapter 5, but the Chapter 5 stuff will be on the next test, not this particular test. So, and to remind you guys of our business application stuff. The big deal is we're talking about trying to maximize revenue and minimize cost, and typically we're focused on something called storage cost. And we had a very special formula for storage cost to remind you. Lot size. In the storage cost world, lot size is going to be your variable X. Now, what exactly is a lot size? A lot size is every time you make an order, how many objects are going to be in that order. Okay? 25, 50, whatever the case may be. Now, in terms of, quote, the average number of items that you're going to be in your inventory, that's your storage, we typically is going to be your lot size divided by 2. And the purpose for this is, the theory is that half your lot size will be out in the public, will be sitting there being able to look this up, grab it off the shelf, take it to the checkout, and buy that stuff. And the other half is sitting in storage, waiting. Once you got to kind of run down on your items, you go get your floor manager out there, and he'll restock the shelves and stuff like that from the stuff that's quote-unquote in storage. And then the number of times a year you're going to order is the total number of, you got to order, the total order. So if you're talking about for the year, how many objects you're going to need for the entire year, divided by X, the lot size, each time you order, how much is going to be in that order. And the big one you need to know is this one. C of X is equal to, which is your inventory cost formula. It's a cost formula, but this one's special. This is your inventory cost formula. Is equal to the storage cost per item times X over 2. That's the stuff that's officially in storage. Plus the cost per order times the total number you ordered divided by X. And if you think about it, total number ordered divided by X, that's the number of, basically the number of times that would be the number of times you're going to be ordering each order, okay? So we did a couple problems last time. We did the one from the Hawks TV example. We also did a revenue type of problem right here where we maximized the revenue, and we needed, about the coffee tables and things like that. So I want to pick up where we left off, which was actually problem number 2 here. It says this: a bookstore is expected to sell 110 calculus textbooks during the next year. It costs $3.75 to store one calculus textbook for 1 year. There is a fixed cost of $8.25 for each order. Find the lot size and the number of orders per year that you'll have to minimize inventory costs. All right? So the first thing is, we got to figure out what we're trying to do here. We're trying to minimize inventory costs. So let's, read problem. Step 2, word problem. Read problem again and pull down the numbers. So in this particular problem we have 110 calculus textbooks. Now, what exactly is that 110? That 110 is the total order. That's what we need. 110 is the total number of textbooks we're going to need for the year. It cost $3.75 to store. So that $3.75 is your, quote, storage cost per item. Storage cost per item. And then we have fixed cost for the order. To reorder, this one's kind of nice. To reorder, we have to basically have one cost, which is $8.25 for each order. For each order. So, the big thing we need to have here is C of X, the inventory cost formula. Again, inventory cost formula is equal to, just to remind you, the storage cost per item times X divided by 2 plus the cost to order times total order divided by X. And X equals what we call lot size. So here's my formula. I'm just recopying what we did before. Now let's plug the numbers that we know into this guy and clean up my equation. So C of X is equal to, what is the storage cost per item? What did they tell us? The storage cost per item was $3.75. That's 3.75 times X divided by 2 plus the cost to reorder. That was a straight cost. It was $8.25 just for each order. Okay? Times, what was the total number we're going to have to order for the year? 110 divided by X. Basically, I'm just plugging my numbers into my formula. Does that make sense? Now, the key word to this formula is minimize. Anytime you need to maximize or minimize, you got to take derivative, set it equals 0, and solve. But before I do that, here's a hint for your next test. Clean up the function first. And this one, I'm going to go ahead and 2 goes into $3.75. Let's see. That'll be 3.75 divided by 2, which is 1.875. So C of X is equal to 1.875 times X plus 8.25 times 110 is 907.5. 907.5 divided by X. One more thing. Clean it up. Again, what's my ultimate goal? You're a calculus student. What are you going to do? Take derivative, set it equals 0, and solve. You've been programmed. If you take derivative, I don't like stuff on the bottom. Anytime I got variables or even functions on the bottom, I like to move those things to the top and make the exponent negative. So this tells me, yep, cost is equal to, this is your inventory cost, equals 1.875x plus 907.5x to the what? Negative 1. Now, take derivative, set it equals 0, and solve. So C prime of x would be equal to, the derivative of 1.875x is 1.875. The derivative of 107.5x to the negative 1. Negative 1 times 107.5 is negative 907.5 x to the negative 2. We're going to set it equal to 0 and solve. But again, now that I'm solving, I want those negative exponents back where they came from, on the bottom. So I get 1.875 is equal to, minus, one step at a time, 907.5 divided by x squared equals 0. I'm going to move this term to the other side. So I get 1.875 is equal to 907.5 over x squared. I added 907.5x squared to both sides, just to let you know what I did. Now I'm going to solve for x. The x squared is in the denominator. So the next move is to get rid of my fractions. I'm going to multiply both sides by x squared. On the right side, it's going to cancel. That leaves me 1.875 x squared equals 907.5. I'm going to divide by 1.875 on both sides and get x squared is equal to, and grab my handy dandy calculator, 907.5 divided by 1.875 is 484. And last but not least, what do I got to do to actually solve for x in this problem? The number of lot size. That would take the square root. And again, officially, when you introduce a square root in a problem, you're supposed to do plus or minus, but this is a word problem. X represents lot size. The lot size is the number of items you're going to have per each order. It's a number that you're going to order. Negative doesn't make sense, so don't do the plus or minus, just do the plus. You're trying to find a solution to the word problem. So the square root of 484 is 22. X equals 22. Does that make sense? But wait, it's a word problem. The last thing you do to any word problem is this. Go back and answer the question. This is how you score on a word problem. You got the answer, 22, great. But now go back and answer in terms of the problem. Now, what did they actually ask in this problem? You're supposed to, quote, find the lot size. So here comes my answers. The answer is lot size. But what does lot size, what does that represent? That's a variable. What is that? X. And what was X equal to? 22. So the lot size is 22. So every time we order, we need to order 22 items. Okay, in this case, 22 calculus textbooks. But there's another part of this one. It says, and the number of orders per year. The number of orders per year, that was one of my little forms. That was equal to the total order divided by X. What was the total number that I had to order? That was 110 divided by X, which is what we saw, which was 22. So, 5. I just want to show you guys on the calculator that I'm not actually cheating on you guys. 110 divided by 22 is 5. So the answer is 22 textbooks we're going to have to order, and we're going to have to order 5 times a year. Does that make sense? Go back and make sure you answer the question. All right, and a similar problem, take a look at this guy here. A jewelry store expects to sell 110 diamond bracelets during the next year. It costs $2.50 to store one diamond bracelet for 1 year. To reorder, there's a fixed cost of $5.50 plus $3.60 for each diamond bracelet ordered. And what is the lot size and how many times per year should we order to be placed to minimize inventory cost? All right. Now, I know you're looking at these numbers and going, wow, where do you get diamond bracelets for $2.50 and $5? No. That's not the cost of the actual diamond bracelet. This is the cost of storing these diamond bracelets under glass in the vault in the back. I understand. All right, so here we go. Step 1, read problem. Step 2, read problem again. A jewelry store expects to sell 110 diamond bracelets. So this is the number we're going to have to order. We're going to order 110 of these guys because that's what we think we're going to be able to sell in the next coming year. The diamond bracelets are in here. It costs $2.50 to store. So this is my storage cost. $2.50 to store each diamond bracelet. Okay? Keep going. To reorder, there's a fixed cost, so to actually to do our reorders, we got a fixed cost of $2.50 plus it's going to cost us, excuse me, fixed cost of $5.50. Look at the wrong number there. $5.50 to order, fixed cost of $5 plus $3.60 per each bracelet we order. Okay? But what's the big question here? What do we want to do? We want to minimize inventory costs. So I need my inventory cost formula. Again, just to remind you, inventory cost is equal to storage cost per item times X over 2 plus the cost to reorder, cost to order times the total order divided by X, which is actually the number of times a year you're going to order. So this is the same formula as what we have memorized, where X is equal to lot size. So plugging my numbers into this thing, what did it cost to store one of these items? $2.50, $2.50 times X divided by 2 plus what was the cost to reorder? Now here it comes. The cost to reorder, we had $5.50 plus $3.60 per each bracelet we order. Every time we order, how many are we ordering? X. X is lot size. X is the amount that we order each time. Does that make sense? That's what X represents. Lot size represents how many are going to be in each, how many in each every time we order, how many in each order. So that'd be $3.60 times X, because of that, per each bracelet. X is the number of bracelets that we order. Times, now how many bracelets are we going to need in the next year? 110 divided by X. Does that make sense? Plugging the pieces of the puzzle into my equation. Now, before I do any weird take derivative, set equals 0, and solve, clean them up. 2 divides into $2.50. What do I get? $1.25. 1.25 times X. Plus, here, I'm going to distribute. So, 5.50 times 110 is 605. That'll be 605 divided by X plus 3.60 times 110. Multiplying this and this, I get 396. But here, what is 3.60x times 110 over x? What happened to the x's? They cancel. That's where I just get to 1.36 times 110. That's where the 396 comes from. So there is my equation, cleaned up. But now I'm going to take its derivative, so I'm going to clean it up one more time, because I don't like stuff on the bottom. So C of x is equal to 1.25x plus 605x to the negative 1 plus 396. Now, I'm going to finally get the calculus, take my derivative. Derivative of 1.25x is 1.25. The derivative of 605x to the negative 1 is negative 1 times 605 is minus 605x to the negative 2. And what is the derivative of 396? 0, because it's a constant. We're going to set this equal to 0 and solve. But I'm going to clean it up. This is 1.25 minus 605 divided by x squared. Negative x goes back on the bottom equals 0. I'm going to move this term to the other side. This gives me 1.25 is equal to 605 divided by x squared. Now I'm going to multiply by x squared on both sides. That gives me 1.25 x squared equals 605. I'm going to divide by 1.25 on both sides. And I get x squared to be equal to, and I'm going to grab my handy dandy calculator and do this. 605 divided by 1.25 is 484, and then I'm going to take the square root of both sides, and I get the square root of 484 is 22. So I have a lot size of 22. But now, don't forget to do this. Go back and answer the question. What was the question on this problem? Well, again, there were two questions here, if I remember. In what lot size? So we got to figure out the lot size and how many times per year. So your lot size, that's your x, which is equal to 22. And how many times a year? How many times per year to order? That was a formula. It was the number of number we have to order, which is 110 divided by x, which is 110 divided by 22, which is 5. So we're going to have to reorder 5 times a year, and the lot size, we're going to order 22 bracelets every time we make an order. That will minimize my storage costs. Does that make sense? Now, here's the deal. You guys have a test coming up pretty soon on this particular type of material. And so to make sure, because my focus also is being the calculus professor, is to focus on the calculus aspect of this thing. So what I was thinking about was I was going to give you guys a problem similar to these problems we just did on your test, on the review here. But I was going to, instead of making you come up with the equation, I was going to write down the equation and actually just plug the numbers in for you, make you clean it up, take it set equals 0, solve. So I'm going to give you the actual equation of the inventory cost, because my focus is calculus. How do you maximize and minimize anything? What are you going to do? Take derivative, set it equals 0, and solve. And then go back and answer your questions. You need to know lot size is X, and the number of times a year you order is the total order divided by whatever that X you just discovered. Okay? You're welcome. So let's move on. Now, if I was also preparing myself for this test, I don't typically do these guys in class on these review questions because those are the ones I want you guys to do. Don't forget about our Friday review session, which we all have it every Friday at 1 o'clock from 1 until 2:15. 12:30. 12:30 until 2:45. Yeah, I get my hours down right. Every Friday. 12:30, because we have the class time. 12:30 until 1:45. I'll show it to you. In Fretwell 113. And I put it up here for you guys, right there, so you can always see it. It's on your Canvas site. The review session is every Friday from there. It is 12:30 until 1:45 p.m. in Fretwell 113. So today, I'll be there. Sandus will be mostly taking over and stuff. She'll be working on with you guys on this stuff. But if you got questions about the particular homework set, we're more than happy to help you out. Questions about the Hawk system and doing problems on Hawks. This is what we did last time, and the first time I actually made a video of it. We typically don't make videos on the Friday review sessions. And the other thing is, if you got questions on these kind of problems over here on the review questions, we'll be more than happy to take a look at these things, because they're going to be, some of them are going to be very similar to what you can expect on the test and stuff like that. But you really need to focus on that review packet I gave you guys that you have to turn in on Monday, because I made up the test, I made up that review packet. So we're moving on though. It's now time for chapter 5. Chapter 5 is on exponential functions, and chapter 5.1 is exponential logarithm functions on chapter 5. Chapter 5.1 is on exponential functions. Chapter 5.2 is going to be on log functions. Now, we are expecting you guys to know this stuff because it's the prerequisite to actually get into this class, exponentials and logs, but we're going to remind you of some things here, because our focus is actually going to be in section 5.3 when we finally take derivative of this stuff. So let's just jump in with both feet and actually start looking at these particular problems here. Now, one of our things, when you go up here and read this stuff about exponential log functions have a wide variety of important applications. For this reason, we are valuable models for the calculus students to study. In this chapter, we'll review these two types of functions, especially with emphasis on the forms of y equals e to the x and y equals natural log of x. So we're going to be focusing on mainly e and natural log with this stuff, but any logs will do. The irrational number e plays a very important role in many real-world applications. E is that 2.71828 number that you know that I've seen before. In this lesson, we will learn about the properties of the exponential function that apply to models using these functions in real-world applications, because you're going to see this stuff again in your future classes, I guarantee it. So, here we go. Let's look at the learn mode here. Now, a function of the form, and I'll go ahead and give you that form, that is f of x, which is equal to c times b raised to the rx. That's how the Hawks folks writes this thing up here. A function in the form f of x is equal to c times b raised to the rx. Now, x is your variable. X is in the exponent of some base b, where b has to be a positive number. So that's what b is a positive real number. B is not equal to 1, because 1 to any power is not very exciting. To be an exponential function, you want a positive base there. And c and r are real constants. This is called an exponential function. Now, we're math people. Don't think too deep in this. Where's the variable located at? It's in the exponent of this base b dot here. Okay? That's why it's called an exponential function. Now, when you look at these two particular guys, there are two different kinds of looks that they're going to have. And I'm going to give you basically the gist of them. If that base has got to be a positive number. If the base b is greater than 0, your exponential function is going to look like this. It'll be called an exponential growth model. Things that grow, money. If you invest money, thanks to interest, you should actually have more money down the road. Okay? Depends on your interest rate, lots of other concepts there, but the goal is to invest to earn interest so your money grows. And this is that growth model that we're talking about. You would have a base bigger than 0. Now, on this particular model, on the left side, horizontal is out, so you have a horizontal axis on the horizontal asymptote, which will be the x-axis, and on the right side it blows up, and it crosses the y-axis right at that point C. So this is your exponential growth model. Now, if you had a fractional base, 0 is less than b, which is less than 1, a classic fraction between 0 and 1. It's still positive, but the look of the graph is going to look slightly different. You will have this reflect across the y-axis look. So here's your y-axis and here's your x-axis. And here's your new y-axis, x-axis. It's still going to go through the point C, but it's going to have this particular shape. When you have a fractional base, you'll have a decay model. Things that decay, well, things like populations sometimes, bacteria populations, radioactive materials. So there's a lot of scientific application of this stuff, but there's also some business applications of this stuff too. If you got some kind of, you're monitoring some kind of company and they seem to be on the decline and you're trying to figure out, okay, when's a good time to get out? Now. But you understand, you're monitoring this stuff. This would be a decay model versus a growth model type thing here. So, regardless of either one of these two types right here, if you look at these guys, let's talk about the classic exponential domain and range of these exponential functions. The domain. What kind of numbers can you put in for exponents? Can you have negative exponents? Sure, we have that kind of stuff all the time. What do you do with a negative exponent? You put them on the bottom, make them positive. So you can have a negative exponent. We've manipulated that. Can you have positive exponent? Sure. Can you have a 0 exponent? What's anything like 5 to the 0 power? No, it's not 0. 5 to the 0 power. Anything to the 0 power is 1. So you can have a 0 power, which means you can have any kind of exponent you want to. So the domain is all real numbers, negative infinity to infinity. However, when you look at an exponential function, when you take a positive base and raise him to that power, you're always going to get a positive number out of it. So your range is from 0 to infinity. You always get positive numbers out of this thing. And you never get quite 0 because it asymptotes or gets very, very close to 0. The x-axis, which is y equals 0, is the horizontal asymptote. Your y-intercept, that point that crosses the y-axis, and it doesn't matter what the base is going to be the point 0c. That's c, which is that coefficient in front. And the last thing here is the x-axis. That x-axis happens to be the, quote, horizontal asymptote. And depends on if you have a base bigger than, excuse me, it should be bigger than 1. That was my fault there. If the base is bigger than 1, it has this. If your base is between 0 and 1, it looks like this. That was my little typo there. The base has to be bigger than 1 to be exponential growth. It has to be a fractional base between 0 and 1 to have that exponential decay. Does that make sense then? Okay? Okay, we got some more little discussions to talk about here. The function is what? What kind of function do we have here? When you look at those graphs, what did you notice? They are continuous. I'm going to go back to your college algebra definition of continuous. I didn't lift my pencil from the paper when I'm drawing these exponential growth or decay models here. Suppose that base B is greater than 1. So we got this B greater than 1. And then C equals 1 and R equals 1. So we're talking about Y equals B to the X, where B is greater than 1. That's going to be your classic growth model. It looks like this. And it actually will cross over here at 1. Okay? Then, if you look at this particular graph, now we are talking about calculus here. The slope is what? As you read a graph from left to right, what kind of slopes does this thing have? Is it going up or is it going down? It's going up, and up means you have a positive slope. It is positive. And Y is increasing. You notice it's getting bigger. And, okay, the second thing is look at your second derivative. What kind of second derivative do I have on these type of exponential with the base bigger one? It is up, concave up. Very good. Now, again, what we were just talking about. If the base is that fractional base between 0 and 1, so the base is a fraction between 0 and 1, we know that's going to be my classic decay graph. So here is 1 here. And it looks like this. And again, this is the equation y equals b to dx, where we have a fractional base here. But in this one, you will notice that the slope is what? As you read it from left to right, which direction is my slope of my tangent line going? It's going down. That means it's going to be negative, which means y is decreasing. But look at that second derivative again. What kind of second derivative do I have? It's still concave which way? Up. And concave up. Now, here comes some formulas you need to know. And I know you guys have covered this for when you do college algebra. It doesn't matter if you took it here or anywhere else. It's a classic formula that you guys need to know. It's a formula for compound interest. So, quote, for a principal P invested at an interest rate R, and we always put the R in decimal form, and compounded n times a year for T years, the amount A, the amount in the account, is going to be given by, and here's your formula, A equals P times 1 plus R over N raised to the NT. This is your classic compounded formula, compound interest formula. P is principal. That's the amount of money you're investing. R is the interest rate in decimal form. N is the number of times a year you compound. So if I compound quarterly, that'll be 4 times a year. If I compound monthly, that's 12 times a year. If I compound annually, that's 1 time a year. If I compound daily, that's 365 times a year. Compounding is how many times a year the bank actually puts money into your account, so you can earn interest on top of interest. Okay? Continuing on, a little show for you guys, the irrational number E. The irrational number E, which is at 2.1828, whatever, is defined to be, and it's the limit as x approaches infinity. Excuse me, x approaches negative infinity. We're going to do that formula. X approaches negative infinity of 1 plus 1 over x raised to the x. So it's a special number that is a limiting value of a limit as x approaches negative infinity of 1 plus 1 over x raised to the x. And this E number is approximately 2.7182882846. It's irrational, so it goes on forever. We will be using the E button on the calculator. The E button on the calculator is located right above the LN button. Just to remind you, it's in blue. So it'll be second E, and it'll be E typically to a power here. So if you get to see this, it'll be E to the, and if you raise it to the first power, anything to the first power is himself. You get E 2.7, 1828, 1828, and there's some more decimals off the screen there. Does that make sense? Okay. Now, if you take this compounding to an extreme, compounding continuously is what you end up getting. That's the best type of compound interest you can ever get. The bank is going to continuously put money in my account. Look, I'm investing money. The more money that I have, the better I like it. And the more times the bank puts money in my account, the better I like it. So if you take this compound interest, instead of 4 times a year, they do it monthly. Monthly will be better. Instead of monthly, they do it weekly, or they do it daily, would even be better. But if you take that to an extreme, hourly, minutely, secondly, nanosecondly, I want the bank putting money in my account. That's called compounded continuously. And that has a special formula, which I know you've seen before. It is the A equals PE to the RT, the famous PERT formula. A is the amount, P that you're going to get back out of the account, P is the principal, the amount of money you're investing, R is your interest rate in decimal form, and T is the time measured in years. Okay? So, let's take a look at this problem right here. So, these two big formulas are what we're going to be focusing on first off here. It says, Mary recently inherited $9,000 and she wants to deposit into a CD account. She has determined her 2 best bets are an account in compounded annually at a rate of 4%, account 1, and an account that compounds daily with an annual rate of 5%, account 2. Which account will pay more interest, and how much will the balance be in the account after 3 years? Round to 2 decimal places. 2 decimal places, typically money to your nearest penny. Okay? So, what do we got? We got account number 1. In account number 1, we got an interest rate of 4%. But for percentages for people who can't do math, what's 4% also known as? Decimal form. Very good. 0.04. Okay? We have a principal of $9,000, so we got $9,000 to invest. Okay? And the interest rate, 4%, and times, because there's time, is 3 years. But here's the deal. This one is compounded annually. Compounded annually. How many times a year is annually? N equals 1. It's 1 time a year. Does that make sense? Now, let's compare that to account number 2 over here. Account number 2, the interest rate on that account is 5%, which is 0.05. The principal is $9,000. She's going to invest it for 3 years. But how much is her compounding? It's going to be compounded what? Compounded how often? Compounded daily. How compounded daily? How many times a year is daily? 365. N's going to be equal to 365. Now, I don't know if you guys know much on business and stuff like that, but number one, when I'm looking for investments and stuff, first thing I'm going to do is try to get my percentage return. I always look at the percentage first. Right now, it's a no-brainer. Which account's better? Second one. And then the next thing I'm going to look at is how many times a year they're going to compound so I can earn that. The more times they compound, the better off I like it. 1 time a year versus 365 times a year, it's a no-brainer. The account number 2 is going to win big time. And you're going to see how big time is in just a second. Let's put the number in. A equals P times 1 plus R over N raised to the NT. A equals, on your first account, is going to be $9,000 times 1 plus your interest rate, which is 0.04, compounded annually, which is 1, raised to the 1 times 3 years. And I'm going to put this into my account, my calculator here. 9,000 times 1 plus 0.04 divided by 1, close parentheses, raised to the 1 times 3. I make it look exactly like the equation I wrote down. And so the amount that I'm going to get back is $10,123.78, rounding to the nearest penny. Does that make sense? Now, how much interest did she actually earn? Remember, interest is the amount of money above what you invested. So the amount over $9,000 is $1,123.78. Does that make sense? Now, compare that to account number 2. Same formula, P times 1 plus R over N raised to the NT. A would equal to 9,000 times 1 plus 5% is 0.05 divided by 365 raised to the 365 times 3 years. So I'm going to type that into my calculator here. 9,000 times 1 plus 0.05 divided by 365 raised to the 365 times 3 years. And I end up getting $10,456.40. What's the difference between these two accounts? I mean, this one would earn $1,456.40 worth of interest, but when you compare the two accounts, it's a no-brainer. This account made what? About $330 more than this account? And now that's called, well, number one, the percentage and the interest rate's higher. But the other thing is, the more times you compound, the better you're gonna like it, because the bank's putting money in your account, so you can earn interest on top of interest. That is the idea of compounding. Does that make sense? So that's your example from your Hawks TV example. Go back and watch the Hawks TV. They're gonna do different numbers and things, but they'll do a similar problem. Take a look at this guy here. It says, Jeff's father is planning to open a savings account to pay for Jeff's college education. He has found a bank that will pay 8% interest compounded daily. How much will he need to deposit so that in 9 years the balance will be $165,000? All right. Now, pay attention and write down what you know. Any kind of word problem. First thing you do is read problem, and then read problem again and write down your numbers. Jeff's father is planning on opening a savings account to pay for Jeff's college education. He's found a bank that offers 8%. If you found a bank that's offering 8% interest, let me know about it. I'll get your name this time. All right, but because right now, what's interest rates going on? What is interest rates at your bank? Seriously. You got a 3% account? My bank's offering me like 0.5% on my checking account and stuff like that. Money market, I'm looking at around 1.5%, maybe 2% at best. But in terms of a classic checking account or whatever, you're getting like 0.5%. You know what 0.5% is? 0.005. We have better rates in World War II than we got right now in terms of investing money. So right now, the only market in town to quote-unquote invest money is the stock market. And the stock market, as it goes up and down, you've got more risk, but you can earn around 8 to 10% interest on something like the stock market. But, you know, yesterday I made some money. Today I lost it. So that's the way the stock market goes. So it's reality for you business majors on it. All right, so we got 8% account, which mathematically is 0.08. Okay. He wants it compounded daily. Compounded daily. How many times a year is compounded daily? So N equals 365 in my formula. We're going to invest it for 9 years. T equals 9. But here he wants the balance will be $165,000. That's what he wants in the future. That's your future value. That's A, the amount in the account later on, $165,000. And the question is, how much does he need to deposit initially? Deposit initially is the original principal. So we want to solve for P in this problem. Does that make sense? So again, writing down your formula. A equals P times 1 plus R over N raised to the NT. 165,000 is equal to P times 1 plus 0.08 divided by 365 raised to the 365 times T, and T was 9 years. Now, before I do all this beautiful math to solve this thing, what are you trying to solve for in this problem? P, right? So you're trying to solve for P. P is right here. To solve for P, I'm going to take this stuff and go ahead and move it to the other side. Okay? Now, you're multiplying. What gets rid of multiplication? Division. Go ahead and get the P by himself. I'm just trying to save you guys some time on sticking on the calculator. So to solve for P, I'm going to divide by this 1.1 plus 0.08 divided by 365 raised to the 365 times 9. And what I do to one side, I do the other. 1 plus 0.08 divided by 365 raised to 365 times 9. This part cancels, so P is going to be equal to, and I'm going to put this on my calculator. So this would be $165,000 divided by parentheses 1 plus 0.08 divided by 365 close parentheses raised to the 365 times 9. And what do I get? $80,320.46. Now I'll have to admit to you guys, on this problem right here, for most of us in the world, this is not a real option for us. You understand what this father is doing? Oh, I'm going to invest in my son's education, and I'm going to need about $165,000 in the future to pay for his college education, and he's obviously about 9 years old now, and when he turns 18 in 9 years, he'll be ready to go to college. So how much money do I need to invest right now to get that $165,000 in 9 years so we can go ahead and pay for his college? His father needs to invest $80,320.46 into this special account. Now, if you've got $80,320.46 just hanging out in an account somewhere, again, see me after class, we'll talk. But this is not reality for most people. How do most people save their money? A little bit at a time. It's called an annuity. Yeah, I saved $100 this month, I get $100 next month, and then over time, it will accrue. Does that make sense? I can't just go, oh, let me go write my kids a check for $80,000 and go put it in a special account so when they turn 18, they can pay for college. That's not reality, but I guess for some people it is, just not most of us, especially me. Does that make sense? Take a look at the next guy. If $9,000 is invested at 10% compounded quarterly, how much will the investment be worth in 9 years? All right, so I got, again, principal of $9,000. The interest rate is 10%. 10% is 0.10. Move the decimal 2 places left. Compounded quarterly. How many times a year is quarterly? 4. And time is 9 years. So again, A equals P times 1 plus R over N raised to the NT. A formula we expect you guys to memorize and know. A is equal to 9,000 times 1 plus 0.10 divided by 4 raised to the 4 times in 9 years, 9. So again, putting this on my handy dandy calculator here, I've got 9,000 times 1 plus 0.10 divided by 4 raised to the 4 times 9, which is $21,892.82. That's how much this money is going to be worth. But this account's paying 10%. Again, you know account paying 10%? See me after class. We'll talk. Because I can definitely get you an A in the class if you can give me a 10% account these days, because this is highly unusual, because stock market doesn't quite pay this kind of stuff. So, all right, take a look at this problem. Here, we got 3 minutes. Hold on, people. In a certain environment, a colony of bacteria grows according to the model A equals A0 e to the 0.19 t, where A is the number of bacteria present in time in hours. After a culture is taken, A0 is the initial number of bacteria. If 200 bacteria are initially present, that tells me A0 is equal to 200. How many bacteria are going to be remained after 10 hours? So my time, because time is measured in hours, is going to be 10. So I'm going to plug it into my account. A is going to be equal to A0, which is 200, e to the 0.19 times 10. And then they want me to round this one to the nearest whole number. So this is 200 times e raised to the 0.19. Notice I hit the e button on the calculator. Times 10. E is right above the LN button, located right there. I kind of showed you that before. And so when I plug that in, how many do I get? I got 137.17888. They said to the nearest whole number. What would your nearest whole number be? 1,337 bacteria. Does that make sense? So again, understanding forms and plugging numbers into the parts of the formula and then crunching them out. That's a big part of what section 5.1. Logarithms 5.2, we'll do that after your test. Remember, reviews due on Monday, test is on Wednesday. See you guys then. And don't forget the review session today, Friday at 12:30. See you guys then.